Hello, welcome back. In the last class, we saw that simplex algorithm is not a polynomial time algorithm. In particular, we saw an example given by Klee and Minty, which showed that if we start from a particular point, then we may end up in visiting all the vertices of the feasible region before reaching the solution, and the number of vertices could be exponential in number, and therefore simplex algorithm is not a polynomial time algorithm. So, therefore, there was a need to devise algorithms which are polynomial time algorithms for linear programs, and which could work well for large dimensional problems. So, in 70s, Khachiyan developed an ellipsoid method, which was the first polynomial time algorithm for linear programming, and in 1984, Karmarkar developed a polynomial time algorithm which has complexity better than that of Khachiyan, and which was performing as well as the simplex algorithm. So, the ideas Karmarkar used were based on the interior point methods. So, as I mentioned in the last class, the interior point methods generate a sequence of points in the interior of the feasible region, and this sequence of points is generated till the final solution is reached. Of course, for a linear program, as we know, the optimal solution exists at an extreme point. So, these interior point methods generate a sequence of points which are in the interior of the feasible region, but they converge to a point which would be very close to the optimal solution, which is a vertex, which is a boundary point. So, as we discussed in the last class, so the idea of the interior point method is that suppose the feasible region is as shown here, and suppose that the extreme point, the solution is at this point. So, this is x star. So, a typical interior point method would start from an interior point and would follow a path which is in the interior, and finally, it will reach a point which is very close to the solution. And the Karmarkar's method was based on some of the novel ideas. So, one of the ideas was that if we have a point so, if this is the direction along which we want to make a movement, or we want to move so that there is an improvement in the objective function. Now, if we have a point which is here, then if we make a movement along this direction, we would reach a point which is somewhere close to the boundary. On the other hand, if we are close to the center of this feasible region, so that means if we are at a point which is somewhere here, and if we make a movement, then you will see that starting from a point which is close to the center, we can make considerable improvement in the objective function compared to any point which is not close to the center of the feasible region. So, it is better to have a point which is close to the center of the feasible region, so that we can make a reasonable improvement in the objective function. So, Karmarkar suggested the following idea, that let us take a a simple feasible region, and let us take any point and let us call it xk. So, Karmarkar suggested to use a transformation to transform this feasible region into some other feasible region in a different space. So, let us call this as the x space and this as y space. Now, this transformation should be done such that the point xk that we have here get transformed to a point which is yk in the y space, such that this point yk is close to the center of the feasible region. And this is done to make sure that the improvement in the objective function is considerable. Now, in the y space, we will need a direction to move, because in the original space the problem was to minimize C transpose x subject to A x equal to b, x greater than or equal to 0. Now, when we use the transformation T to project these points in the y space, the variables x get changed to y, and this will become a problem in the y space. And in the y space, we need to find out what is the direction dk along which we need to move. Now, if we look at the x space, as I mentioned in the last class, that the idea is to use nonlinear programming algorithms to solve this problem, and therefore, since the objective function is continuously differentiable, steepest descent direction is the best choice or the preferred choice. So, if we move along the steepest descent direction, then we may leave the feasible region. So, what we need to do is that we need to project the steepest descent direction onto this set. Now, when we transform the original problem into a new problem, which need not be a linear program, how do we find the direction or the steepest descent direction in the new space which is projected onto the constraint set? So, that is the first question that we would like to answer. Now, having found the direction to move, then the next step is to find alpha k. So, that we would have yk plus 1 is equal to yk plus alpha k dk, like what we had in our discussion on the unconstrained optimization problem, that the new point is formed using the current point by moving along the direction dk with a step length of alpha k. Remember that this quantity alpha k is greater than 0. So, from yk, so suppose we get a direction dk to be this. So, we make a movement of make a movement of alpha k along the direction dk. So, remember that this is the direction dk and we need to move along this direction so that we do not cross the boundary. So, we would reach a point which is going to be yk plus 1. So, this point yk plus 1 is obtained based on the current value of alpha k and the direction dk. Now, having reached a point which is close to the boundary, we need to see what is the corresponding point in the x space. So the corresponding point, to find the corresponding point, we need a map which is from the y space to the x space. Let us call that map as T inverse. So, the map T that we get should be invertible. So, that means that from x k we go to point y k, from y k we make a movement along the direction d k with a step length of alpha k, and from y k plus 1 we come back to a point which could be x k plus 1. So, we have made a movement in this direction. Now, suppose that this point was optimal. So, that means you will see that we have made a movement towards the direction of the optimal point. So, note that this movement did not be in a straight line, as I showed earlier. One could have a movement which could be represented by an arbitrary curve towards the final point. So, once we find x k plus 1, then again we use the transformation T. Now, this time a new feasible region would be formed in the y space, and from that feasible region we find out the point y k plus 1. So, that point will be different from this, because now we have used a different T based on the current value of x k plus 1, and this procedure is repeated. So, finally, we may get a path in the input space which could be something like this, and finally, we will go close to the solution. So, this was the idea proposed by Karmarkar in his projective scaling algorithm. Now, his algorithm was modified to devise an affine scaling algorithm, which is which uses a very simple transformation T. So, in today's lecture, we will first see the affine scaling algorithm, which was an extension of Karmarkar's algorithm. Note that Khachian's algorithm was a polynomial time algorithm. Karmarkar's algorithm was also a polynomial time algorithm, but the affine scaling algorithm is not a polynomial time algorithm for solving linear programs. But nevertheless, it is useful to understand some of the concepts that were used in Karmarkar's algorithm. So, let us look at the affine scaling algorithm to solve linear programs. So, as I mentioned that in the interior point methods, the points are generated in the interior of the feasible region, and they are based on nonlinear programming techniques like steepest descent method. And chronologically, Karmarkar's method was developed first and then the affine scaling algorithm, but we will study affine scaling method first before moving on to Karmarkar's method. So, we will continue to consider the standard linear program, minimize C transpose x subject to x equal to b and x non-negative, with the assumptions that A is a full row rank matrix, A is a matrix of size m by n. So, affine scaling method uses the idea of projected steepest descent direction at every iteration. So, suppose we are given a feasible point which is in the interior of the feasible region at the current iteration k. Since the point is feasible, it satisfies the constraints x k equal to b and x k greater than or equal to 0. So, we have x k equal to b and x k greater than or equal to 0. Now, suppose we want to move along the direction d. So, x k plus 1, let us assume that x k plus 1 is x k plus d. Now, the ideas which I am going to talk about, they also hold in the y space. Although I am discussing everything related to the x space, these ideas also work for the y space. So, let us assume that the step length is of size 1. So, alpha is 1. So, x k plus 1 is equal to x k plus d. So, if we have a point x k and we have a direction d, we take a suppose a unit step along this direction to move to the point x k plus 1. Now, the new point also should satisfy this constraint. So, we also need to have a x k plus 1 is equal to b and x k plus 1 greater than or equal to 0. So, therefore, a x k plus d should be equal to b and x k plus d should be greater than or equal to 0. So, since we already have a x k equal to b, so what we get is a d is equal to 0 and x k is already greater than or equal to 0. So, we get d greater than or equal to 0. So, the direction that we are going to choose should be such that that should be in the null space of the matrix A, and moreover all its components have to be non-negative. Now, this requirement can be typically handled using the algorithm. So, let us not worry about this at this moment. Let us mainly concentrate on the fact that the direction d along which we should move should be in the null space of the matrix A. So, suppose we have some direction along which we need to move. For example, it could be a steepest descent direction. Now, a steepest descent direction may not ensure the feasibility. So, what we need to do is that we need to find the null space of the matrix A and project this steepest descent direction onto. So, this space is the null space of the matrix A. So, null space of the matrix is the set of all directions d such that A d is equal to 0. So, if we have any direction along which we need to make a movement, first we need to project that onto the null space of the matrix A. So, how to do that, that we will see now. So, if we choose a step length alpha k where alpha k is positive, then x k plus 1 will be denoted by x k plus alpha k d, and therefore, a x k plus 1 equal to b, that is x k plus 1 is a feasible point, implies that a d equal to 0. So, in the affine scaling method, it is proposed to use projected steepest descent direction. So, which is the projection of the steepest descent direction minus c on the null space of the matrix A. So, let us see how to do that. So, let us call this as c hat, and c hat is nothing but suppose minus c. So, this is the steepest descent direction, because the objective function is c transpose x. So, the gradient of the objective function is c and the negative of the gradient is minus c. So, this is the steepest descent direction minus c, and which we want to project it onto the null space. So, let us denote this component by PC, projection of the steepest descent direction. Now, we know that there is a space which is orthogonal complement of null space of A, and that is, this space is called the row space of A. So, any vector C, C hat, which is in the n dimensional space, can be split into two parts. One is the projection. So, this is the orthogonal projection of C hat onto the null space of A, and then the other component will be the projection in the projection on the row space of A. So, let us call this as Q. So, C hat can be written as P C plus Q. Note that the two spaces which are mentioned here, row space of A and null space of A, they are orthogonal complements of each other. So, C hat can be uniquely represented as P C plus Q, where P C denotes the component of C hat on the null space of A, and Q denotes the row space of A. Now, since P C belongs to the null space of A, what we have is A P C equal to 0, because it satisfies this property, and Q belongs to the row space of A. So, Q can be written as A transpose lambda. Now, given C hat, we want to find out what is P C. Now, for that purpose, we first need to find out what is Q, and Q is nothing but A transpose lambda, but for finding Q, we need what is the value of lambda. So, let us use this fact to find out the value of lambda. So, if we multiply throughout by A, so what we get is A C hat is equal to A P C plus A Q is nothing but A transpose lambda. Now, this quantity is 0. So, therefore, since A is a full row rank matrix, we can write lambda to be A transpose inverse A C hat. So, this is the value of lambda that we get. Now, we can write C as, therefore, C hat can be written as P C plus Q. Q is A transpose lambda. So, A transpose inverse A C hat. So, this is the vector C hat obtained as a combination of P C plus Q. So, we know A, the matrix A, we know C hat. So, it is easy to calculate this quantity, and therefore, P C, which is the projection of the vector C hat on the null space of A, is nothing but C hat minus A transpose inverse A C hat, and this is nothing but identity matrix minus A transpose inverse A into C hat. Now, C hat is nothing but negative of C. So, this can be written as minus identity minus A transpose inverse A to C. So, this matrix, what we get here, this is called the projection matrix. So, this matrix projects C onto the null space. So, with the projection of minus C will be as shown here. So, we can write this as minus P C. Now, this capital P, this is a projection matrix and C is a vector. Remember that this small p, lowercase p is a component of C hat on the null space of the matrix A. So, given a direction D, which could be a steepest descent direction, we can use projection matrix to project it onto the null space of any matrix using this formula. So, as I mentioned that if we denote C hat to be minus C is the negative descent direction, and it has two components P C and Q, where P C belongs to the null space of A and Q belong to the row space of A, and therefore, A P C equal to 0 and A transpose lambda equal to Q, and using the fact that A C hat is equal to A P C plus A Q, A P C is 0. So, A Q is nothing but A transpose lambda, and since A is a full row rank matrix, A transpose becomes invertible, and therefore, we get a value of lambda which can be used to find out Q, and therefore, using P C equal to C hat minus Q, what we can do is that we can write it as C hat minus A transpose inverse A C hat, and this is nothing but minus P C, where the matrix P denotes the projection matrix. So, any direction can be projected onto the constant set using the projection matrix. Now, the second idea that is used in affine scaling method is the positioning of the current point which close to the center of the feasible region. So, if the current point x k in the x space can be projected using some transformation t to the point or to a point which is close to the center of the feasible region. So, in affine scaling, a preferred choice for this point which is close to the center is the point where all the coordinates are 1. So, all the coordinates have equal values, and that is a preferred choice in affine scaling to be the point close to the center of the feasible region. So, if we are given a point x k in the interior of the feasible region in the x space, so let us define a matrix x k to be having a diagonal structure where each entry in the diagonal represents one of the components of the vector x k. Now, having defined the matrix, let us define the transformation y, transformation t as y equal to t x, where t x is nothing but x k inverse x. So, you will see that since x k was obtained by placing the diagonal entries of the vector x, by placing the entries of x along the diagonal of the matrix x k inverse x will be a unit vector or the vector of all ones, and therefore, y k will be x k inverse x k will be a vector of all ones. So, by defining this transformation, we were able to get for any x k, by defining the matrix Sk to be diagonal of Xk, the point in the Y space for the feasible region will have all the entries equal to 1. And note that Xk's are all greater than 0 because the given point Xk is in the interior of the feasible region. So, Xk's are all greater than 0. So, this inversion is also possible, and because of which we can write xyk as xk, xkyk as xk. So, given x, we can use this transformation T to convert it to the Y space. So, Y is nothing but xk inverse x, and given Y, it is easy to transform it back to the original space using xky is equal to x transformation. So, now let us look at a general idea of affine scaling algorithm. So, we start with any interior point x naught. Now, while some stopping condition is not satisfied at the current point, the algorithm first transforms the current problem into an equivalent problem in Y space. So, note that this is very important, that we should have an equivalent problem in the Y space. We may not always have a linear program in the Y space, but we should have a program in the Y space or the problem in the Y space which is an equivalent to the original problem. And this transformation should be such that the current point is close to the center of the feasible region. We then use projected steepest descent direction in the Y space to take a step in the Y space, so that we do not cross the feasible set boundary. So, this is very important, that the yk that we get, yk plus 1 that we get from the current yk should be feasible. So, therefore, the step should be taken such that we do not cross the feasible set boundary. Now, once we find yk plus 1, we need to find out what is xk plus 1. So, we need to map that point yk plus 1 back to the original space. So, map the third step is to map the new point back to the corresponding point in the x space. Now, this procedure is repeated till stopping condition is satisfied. So, there are few important points that need to be discussed. The first one is that what is the stopping condition for the program. Now, in the simplex algorithm, we saw that since the solution always lies at the extreme point for a linear program, we saw that if at a point all the neighboring vertices have an objective function value which is not less than the current point, then we stop. So, that stopping criterion was easy to check. Now, here since we are not talking about the vertices in this algorithm, we need to find out some condition which could be satisfied at optimality. So, that is the first part. We have already seen what is the what could be a possible transformation to move the current point to a point in the Y space which is close to the center of the feasible region. We also saw how to project a steepest descent direction in the given space. So, let us first see what is a good stopping condition for this algorithm. Now, the duality ideas for linear programming that we discussed earlier, they become very useful while designing many of the algorithms. So, we will see one such condition which could be used as a stopping condition for an affine scaling algorithm. So, let us consider the linear programming standard form and the corresponding dual. Now, we have seen that because of the weak duality, if x is primal feasible and mu is dual feasible, C transpose x is greater than or equal to B transpose mu. So, given x and mu which are primal and dual feasible, we know that the primal objective function value is at least the dual objective function value, and moreover at optimality there exists x and mu such that C transpose x is equal to B transpose mu at optimality. As I mentioned earlier, that this is also called duality gap, the difference between the primal objective function value and the dual objective function value, where the primal is in the form minimize the objective function and dual is of the form maximize a corresponding objective function. The duality gap represents the difference between the primal and the dual objective function value at feasible x and mu. So, at optimality the duality gap is 0, and that could be used as a stopping criteria for our algorithm. Now, that means that we need to find the value of mu, and as we will see that the KKT conditions can be used to find the value of mu corresponding to the value of x. So, let us see how to do that. So, the weak duality ensures that the primal objective function value at any feasible primal point is at least the dual objective function value at the corresponding dual point mu, and at optimality the two are equal, and that is called strong duality. So, the question so the idea is to use the duality gap C transpose x minus B transpose mu to check optimality, and the question is how do we get mu, and for that purpose let us make use of the KKT conditions. So, let us consider this standard linear program and define the Lagrangian to be C transpose x plus mu transpose B minus A x minus lambda transpose x. Now, let us assume that x is primal feasible and lambda is non-negative. Now, if we write down the KKT conditions at optimality, one of the conditions is the gradient of the Lagrangian with respect to the primal variables is 0. So, gradient of the Lagrangian with respect to x is 0. So, if we take the gradient of this Lagrangian function, it will be C minus A transpose mu minus lambda. So, that will be equal to 0. So, therefore, A transpose mu plus lambda equal to C. So, this condition needs to be satisfied at optimality. Now, we have two variables mu and lambda which need to be determined, but the complementary slackness conditions become very useful at this moment. So, the complementary slackness conditions say that lambda I xi should be equal to 0 for all I going from 1 to n. So, which means that if a particular xi is greater than 0, then the corresponding lambda has to be equal to 0, and therefore, we can combine these two conditions together to write that by defining a matrix X which is a diagonal of X. So, we take a vector X and put its components along the diagonal of a diagonal matrix and form a matrix X. Then the KKT conditions can be written as X into C minus A transpose mu should be equal to 0. So, if X is greater than 0, then the corresponding lambda has to be 0 because of the complementary slackness condition, and that lambda is nothing but the component of C minus A transpose mu. And if x equal to 0, we have xi lambda I to be 0. So, xi into the corresponding component of lambda is 0. So, this condition needs to be satisfied at optimality. Now, that condition can be used to determine the value of mu. So, what we need to do is that we need to minimize, remember that the minimum quantity of this expression is on the left side is 0. So, we need to minimize xc minus x A transpose mu subject to mu, so as to get the current value of mu. So, we minimize the norm square of xc minus x A transpose mu. Now, if we differentiate, so before differentiating, let us note that mu is unrestricted in sign. So, this becomes an unconstrained optimization problem. So, we have a convex function which is differentiable, and differentiating with respect to mu, what we get is mu is equal to Ax square A transpose inverse Ax square equal to x square c. So, this is the value of mu. Note that the current point x is part of the matrix X, because the matrix X was formed using the current variable x. So, given x, we first form a matrix X and then use this formula to find out mu, and therefore, the duality gap at x k will be C transpose x k minus B transpose mu k, where mu k is obtained using x k and x k is obtained using the current iteration vector x k. So, the matrix x k is obtained using the current iteration vector x k. So, mu k is nothing but A x k square A transpose inverse x square c, where x k is the diagonal of the matrix x k. So, x k can be used to find out mu k, and then C transpose x k minus B transpose mu k gives us the duality gap. And therefore, the stopping condition for an algorithm could be that C transpose x k minus B transpose mu k is greater than 0, because duality gap is always greater than or equal to 0, and the algorithm would terminate when the duality gap is equal to 0. Now, the next step is after studying the stopping condition, the first step that we saw in the algorithm was to get an equivalent problem formulation to get considerable improvement in the objective function. So, given x k, we define the matrix x k to be the diagonal matrix having elements x k on its diagonal, and we define the transformation y equal to T x as x k inverse x, and therefore, if we use this transformation, then what happens to the linear program that we get or that we wanted to solve. So, in the y space, this program becomes minimize C transpose x k y, because x is nothing but x k y. So, minimize C transpose x k y subject to A x k y equal to b and y greater than or equal to 0. So, this is our new linear program. Remember that this is a linear program, because the objective function and the constraints are all linear in terms of the variable y. So, the variable is now y, and this is still in the standard form, because we can combine C transpose x k to be C bar transpose and A x k to be A bar, and therefore, it still remains a program in the standard form, where C bar is x k c and A bar is equal to x k. So, by using this transformation, we still retain the program as a linear program, but now the descent direction will be negative of C bar, which is nothing but minus x k c. So, that will be the descent direction that will be used, and the matrix A, which was in the original space, will now correspond to a matrix A x k in the y space. So, what we would be interested in finding out the negative of x k c direction on the null space of the matrix A bar, where A bar is nothing but A x k. So, the projected steepest descent direction and the determination of step length is the next step of the algorithm, and let us recall that in the y space we work with the variables, we work with the variable y with the constant vectors c bar and a bar and b which are given to us. So, we have this transformation given x k, y k is nothing but x k inverse x k, and that is nothing but a unit vector in the y space, and the projected direction of the negative of the c bar on the null space of a bar by using the same ideas that were discussed earlier, we can write it as a decay to be the negative of the projection matrix into x k c. So, this will be the direction along which one can make a movement by retaining feasibility, but then how much progress can be made or how much movement can be made along the direction dk, so that we do not cross the feasible set boundary. So, that is the next question that we would like to answer. Now, if alpha k, which is the positive quantity, denotes the step length, then y k plus 1 should be equal to y k plus alpha k dk. Now, this note that we want y k plus 1 to be in the interior of the feasible region. So, that means that y k plus 1 should be strictly greater than 0. Now, y k, which is the current point, is greater than 0. So, what we want is that y k plus alpha k dk should be greater than 0, or 1 plus alpha k dk should be greater than 0. Now, we have y k plus 1 is equal to 1 plus alpha k dk. So, on the horizontal axis we have alpha, and on the vertical axis we have y k plus 1. Now, y k plus 1 is of the same dimension as x, which is n. Now, y k plus 1 will have n components, and the different components vary in a different way based on decay. Now, some components could vary like this, some component could vary like this, and some component could vary like this. So, you will see that at this point a particular component of y becomes 0. And then it will go to a negative quantity as alpha is increased further. So, we check the different values of alphas at which different components of y k plus 1 go to 0, and among them we choose the least one, and this we will call it as alpha max. So, the maximum step length could be alpha max, and that will correspond to taking one of the points to 0, and we do not want to take a point which is on the boundary. So, alpha k will be chosen as some multiple of alpha max, so that all the components of y will remain positive at that value of alpha. So, typically 0.9 is a good choice for that. So, 0.9 into alpha max could be a value of alpha k. So, we want this to be greater than or equal to 0, and therefore, alpha max is chosen as minimum of minus 1 over dk, dkj, where dkj is less than 0. and this alpha k is set to 0.9 into alpha max. And the step 3 of the algorithm is to transform yk plus 1, which is obtained here, back to the x space, that is xk plus 1 is nothing but xk yk plus 1. So, now we have an affine scaling algorithm to solve an LP in standard form. I reiterate here that this is not a polynomial time algorithm, but it gives us an easy way of implementing some of the ideas that Karmarkar proposed in his projective scaling algorithm. Of course, the transformation that Karmarkar's algorithm uses is different, and we will see that sometime later, but right now we have used a simple transformation, and that resulted in a simple linear programming in Y space, and therefore, we studied the affine scaling algorithm first. So, we are given a linear programming in standard form. So, the values of a, b, c are known. x0 is a initial point which is arbitrary in the interior of the feasible region. Epsilon will be used for finding out the stopping condition. So, the iteration counter is set to 0. The matrix xk is set using the diagonal matrix xk is set based on the values of the corresponding components in the vector xk. The dual variable mu k is found using the formula that we saw earlier. Now, the first step is that while stopping condition is not satisfied, so which means that while the duality gap is greater than some epsilon, where epsilon is a user given parameter, the project the negative steepest descent direction. So, project minus c bar on the null space of a bar, and this is the expression that one gets, and we saw this earlier. Now, having done this projection, we need to find out the step length that could be used. So, the step length which one can use is 0.9 times the minimum at which one of the component becomes 0, or 0.9 into alpha max. So, this is the alpha max that we have, and then transform the point back to the original space. So, this space, this step first does yk plus 1 is equal to yk plus alpha k dk, and then xk yk or xk plus 1 is equal to the matrix xk into yk. So, this is nothing but yk, and the 1 here indicates that it is a yk is equal to 1 in the Y space, and that is added to alpha k dk. Dk is the negative of the steepest descent direction projected on the A bar matrix, the null space of the A bar matrix. And then we get ready for the next iteration. So, the matrix xk plus 1 is set to this quantity, and mu k plus 1 is found, because that will be used to check the stopping condition. The iteration counter is set to 1, and then we go back and check whether the stopping condition is satisfied. Finally, when the algorithm terminates, we get x star, which is equal to the current value of xk, and this point will be typically close to the vertex, which is a solution point of the linear program, because at every time we are ensuring that we do not cross the boundary. So, we may not the algorithm path may not generate a point which is a vertex, but we will get a point which is close to the vertex. So, if we apply this affine scaling algorithm to this problem, we have already seen this problem when we discuss simplex method, and we know that the solution is 1, 1. So, if we start with a point 0.6, then here are the iterates generated using the affine scaling algorithm that we saw, and the last column denotes the distance between the current iteration point and x star, the Euclidean distance, and you will see that the distance of the current point from x star keeps coming down as the algorithm makes progress. So, after 4 iterations, you will see that the distance between the two is only 0.10 or 0.10. So, this gives us some idea about how the affine scaling algorithm works. Now, here is a plot. So, this quadrilateral denotes the feasible region, and we start from a point which is having x1 and x2 to be 0.6, and this is the solution point which is 1, 1, and this is how the algorithm makes a progress after 4 iterations. Okay. So, this gives us some idea about how an affine scaling algorithm works. Now, we will see the different transformation used by Karmarkar in his algorithm to solve linear program, and also the form of the linear program which is needed for Karmarkar's method. In the last class, we discussed about affine scaling algorithm. So, the idea was that in the X space we had this constraint set, and the idea is to use some transformation T to transform this constraint set into Y space, so that the point x k gets mapped to a point y k which is close to the center of the feasible set. So, the reason for this is that if our current point is close to the center of the feasible set, then a considerable improvement in the objective function is possible. So, that is the idea behind this transformation. So, one moves along the projected steepest direction. So, suppose this is the projected steepest direction. So, one moves till one hits the boundary of the feasible region. Now, once this point, so this is the direction decay, and the step length is chosen such that one does not cross the boundary. So, just before hitting the boundary of the feasible set, one finds out an appropriate step length, so that a new point y k plus 1 is found, and then that point is mapped back to using the transformation T inverse. So, we need an invertible transformation, and that new point could be a corresponding point x k plus 1 in the input space. And again, once at x k plus 1, one defines a new transformation T. So, this transformation T does depend upon the current point. So, it is not a constant transformation, it is not a transformation which is independent of x. So, this was the main idea of affine scaling algorithm, and the reason why we studied this algorithm first was that it is simple and easy to understand. So, the main idea was that while the duality gap is not small, find the direction decay. So, which is the projected steepest descent direction, projection of the steepest descent direction on the null space of the matrix A. So, since the problem is transformed to Y space, one has to project x k c on the null space of the appropriate matrix, find the step length, so that one does not cross the boundary, then get x k plus 1 using the value of alpha k and d k and the current value of x k, and find x k plus 1, the matrix x k plus 1 using the vector x k plus 1 by putting those entries of the vector in the diagonal of the matrix, find mu k plus 1 to find out the duality gap for the next iteration, setting k equal to k plus 1 and going back to the step previous step where we check whether the duality gap is small enough. So, this is the idea of affine scaling algorithm, and we saw in the last class that the points generated are in the interior, and this was the plot for the 4 iterations of affine scaling algorithm. Now, with this background, we move on to Karmarkar's algorithm. Now, Karmarkar's algorithm or Karmarkar's method makes certain assumptions about linear program. So, let us first see those assumptions and then study some of the important steps that were used by Karmarkar's method. Again, I repeat that Karmarkar's algorithm was developed first, and affine scaling algorithm was developed as a modification of Karmarkar's algorithm. Karmarkar's algorithm is a polynomial time algorithm to solve a linear program, while affine scaling algorithm is not a polynomial time algorithm to solve a linear program. But nevertheless, it was simple to understand affine scaling algorithm before moving on to Karmarkar's method. Okay. So, the first assumption that Karmarkar's method makes is that the linear program is in homogeneous form. So, you will see that in the constraints there is no b involved here on the right side of this system of equations. So, we have the linear objective function to be minimized subject to x equal to 0, and this 1 is a vector of all ones. So, the sum of all elements in x is 1 and x is non-negative. So, this is not a serious this is not a assumption which will be violated at every point of time. On the other hand, there are ways to convert linear programs in standard form to the homogeneous form. So, we will continue to use this homogeneous form when we talk about Karmarkar's method. It is not a serious drawback of Karmarkar's algorithm. Now, the second assumption is that the optimum objective function value is 0. Now, if one has some knowledge about duality and dual functions, then one can appropriately choose the dual function so that the duality optimum objective function value can be assumed to be 0. So, these are not serious drawbacks of Karmarkar's algorithm, but these assumptions make the algorithm simple. Now, as is the case in the case of affine scaling method, the idea here is to use some transformation to move an interior point of the feasible set to the center of the feasible region. Okay. So, as was done in affine scaling, here also one needs to use the projective transformation to move a point. Now, in affine scaling, we moved the input point to the point which contain all ones in the y space. In the Karmarkar's method, the point is moved to a point where in n dimensional space every coordinate has a value 1 by n, and then as was the case in the case of affine scaling, we move along the projected steepest descent direction. So, finding a transformation to move an interior point to the center of the feasible region and moving along the projected steepest descent direction are two key aspects of Karmarkar's method, and all these are done with respect to this problem formulation, which is the linear program in homogeneous form, and under the assumption that the optimum objective function value of this program is 0. Now, as I said that there are different ways to convert a linear program in standard form to this homogeneous form. So, this is not a serious drawback of Karmarkar's method. Now, let us look at the projective transformation used in Karmarkar's method. Now, let us consider the transformation T, which is defined by Tx equal to xk inverse x by 1 transpose xk inverse x. So, xk is a matrix, is a diagonal matrix obtained by putting the elements of the vector xk along the diagonal of the matrix xk, and of course, we are assuming that x is not equal to 0. So, suppose we consider this transformation, then you will see that 1 transpose y, where 1 is a vector of all ones. So, 1 transpose y will be nothing but 1 transpose xk inverse x by 1 transpose xk inverse x, and that is equal to 1. So, any point x gets mapped to the center of the feasible region in the y space. So, when we consider a mapping from x to y, you will see that y has coordinates 1 over n for all n dimensions, and 1 transpose y equal to 1. So, this transformation lets us to map x to y such that y is the center of the feasible region. Now, it is easy to derive a inverse transformation for this. Now, from this expression, we can write x to be, so if we multiply throughout by xk and multiply this equation by 1 transpose xk inverse x, so what we get is x equal to 1 transpose xk inverse x into xk y. Now, we want to write x in terms of y. So, we have to get rid of this x from this expression and write it in terms of y. So, let us see how to do that. Now, 1 transpose x will be nothing but 1 transpose xk inverse x into 1 transpose xk y. Now, 1 transpose x, we have assumed that 1 transpose x equal to 1, because that is the one of the requirements of homogeneous linear program. So, 1 transpose x equal to 1 means that 1 transpose xk inverse x is equal to 1 over 1 transpose xk y, and therefore, we are able to write 1 transpose xk inverse x in terms of 1 transpose xk y. So, substitute this value here, and what we get is T inverse y will be x equal to xk y, this quantity, and 1 transpose xk inverse x will be 1 over 1 transpose xk y. So, that quantity is in the denominator. So, we are able to get a inverse transformation. So, one can check that this transformation T is now a 1-1 invertible transformation. Now, if you use this transformation, then the original linear program, which was in homogeneous form, now substitute x here, x as xky by 1 transpose xky in this homogeneous linear program. So, we get a program in y space, and that program would look like this, where x is replaced by xky by 1 transpose xky. So, the objective function, this value is replaced, ax equal to 0 will be converted to axky equal to 0, and as we saw, any point x is converted to y such that 1 transpose y is equal to 1, and y's are greater than or equal to 0. Now, for a moment it may appear that a simple linear program has been converted to a program which is not linear. For example, the objective function itself is a fraction of 2 linear terms. So, it is not a linear program, and therefore, it will be difficult to solve this. But if you look at the denominator, note that xk was greater than 0. So, all the entries in this matrix are positive. Y is also a point which is in the center. So, y is also positive. So, 1 transpose xky is a positive quantity, and not only that, it is also bounded. So, this program can be equivalently written in the form minimize C transpose x k y subject to the same conditions. So, we have gotten rid of the denominator here mainly because the denominator here is a positive quantity and bounded quantity, and therefore, minimization of this fractional form of objective function is equivalent to minimization of the numerator, since the denominator is positive and bounded. The other constraints remain the same. So, the original linear program, which is in homogeneous form, is now converted to another linear program in the y space, which is also in homogeneous form. Okay. So, now we have to solve this program using the steepest descent, using the projected steepest descent method. Now, as I said earlier that the equivalence of these two is possible because of the assumption that optimal objective function value is 0 and 1 transpose x k y is greater than 0. So, we now see how to get a descent direction for this homogeneous linear program in the y space. Now, the gradient of this objective function is x k c, and the negative of the gradient is minus x k c. So, that is the steepest descent direction, but then we have to project that direction onto the null space of the matrix A x k and 1 transpose put together, and we also have to make sure that d is greater than or equal to 0. So, the first step is to get a projection of the steepest descent direction minus x k c onto the subspace where d satisfies A x k d equal to 0, 1 transpose d equal to 0 and d is non-negative. So, it is easy to see this because so, suppose d is the direction that we are looking for along which we make a movement. So, we write the problem in terms of d. So, it will be minimize C transpose x k y plus d. Minimize C transpose x k y plus d subject to A x k y plus d equal to 0, 1 transpose y plus d equal to 1 and y plus d greater than or equal to 0. Now, C transpose s k y, this quantity is already, it should be y k, because y k is the current point. So, C transpose x k y k is a constant quantity. So, we will be interested in minimizing C transpose x k d subject to A x k d equal to 0, 1 transpose d equal to 0 and d greater than or equal to 0. Now, so the way it is done is the following, that we first solve d by minimizing or getting the projection of xkc on the null space of axk, and the projection of xkc on the null space of axk is obtained by minimizing norm of xkc minus d square subject to the constraint that xkd equal to 0. So, we have taken care of the first part. Then after having obtained that d, one projects it on the null space of the matrix 1 transpose, and then using the algorithm we make sure that d is greater than or equal to 0. So, if we do this, then we will have found the projected steepest descent direction of minus xkc in the y space. So, let us do this first. Now, if you consider the problem to minimize norm of xkc minus d square to get the projection of xkc on the null space of axk. So, we write the Lagrangian. So, the Lagrangian variables are the variables of the original problem as well as the Lagrange multipliers associated with the equality constraint. So, the objective function plus mu transpose axk d, that will be the Lagrangian. So, getting the gradient of the Lagrangian with respect to d and setting it to 0, what we get is minus xkc minus d plus xk transpose mu equal to 0, and this gives us d to be xkc minus xk transpose mu. Now, remember that d and mu are the variables, and we have d written in terms of mu. Now, this d also should satisfy the feasibility. So, axk d equal to 0. Now, if we multiply this equation throughout by axk, then the left side becomes 0, and we will get mu in terms of a, xk and c. So, multiplying throughout by axk, what we get is axk square c minus axk square a transpose mu equal to 0, and this equation can be used to find mu. So, since A is a full row rank matrix, we can invert axk square a transpose and multiply that, post multiply by ax square c to get mu. And once we have this value of mu, we plug in that value of mu here, and we get the expression for d. So, finding d which solves this problem is easy, and then one has to get the projection of minus d on the null space of 1 transpose. So, if we take the projection of minus d on the null space of 1 transpose, so this is the projection matrix I minus 1 by n 1 1 transpose, where 1 is a vector of all 1s into the direction xkc minus xk transpose mu, where mu is obtained using this. So, first we obtain mu, plug in that value of mu here, and we get the projection of minus d on the null space of 1 transpose. Now, here we will have to use those entries which are not negative. So, this will be the direction along which we move. So, the entries which are not negative can be obtained using a simple algorithm. So, here is Karmarkar's projective scaling algorithm, where the input to the algorithm is a homogeneous linear program, and we have the matrix A, which is a full row rank matrix, vector C in the objective function, and some epsilon used for stopping criteria. Remember that one of the assumptions that Karmarkar's algorithm used was that the minimal objective function value is 0. So, we can use epsilon instead of 0 to check whether the optimality has been reached. Of course, in the original algorithm, the stopping criteria used was different, but just for understanding, we have put C transpose xk greater than epsilon to be the stopping condition for Karmarkar's algorithm. One can look at original paper of Karmarkar to see the stopping criteria used by that algorithm. Okay. So, the iteration counter is set to 0 initial point is taken to be the center of that feasible region. The matrix xk is set. So, while the optimum objective function value is not close to epsilon, one finds the projected steepest direction dk and then makes a movement in the y space along that direction. So, this is the current point which is also 1 by n, and then so current point plus alpha k dk. So, this is the normalized projected steepest descent direction dk by norm dk, and that is multiplied by alpha k. So, Karmarkar found that a good choice for alpha k is 1 by 3 into root of n into n minus 1. So, one finds a new point y k plus 1, and then the next step is to project it back to the input space x space, and that is done using the inverse transformation T inverse. And the new matrix x k plus 1 is found, iteration counter is increased, and one goes back to the new point and check whether optimality is satisfied. So, this procedure is repeated till optimum value is satisfied, or the procedure is repeated till the current point x k is very close to the optimal value, because with this condition we cannot truly reach the exact optimal point, but we will be or the algorithm will be very close to the optimal point. So, when the algorithm terminates, we get the x star to be the current iteration value of x. So, this is the rough idea about Karmarkar's algorithm, which was the first algorithm which was polynomial time and also efficient than Khachiyan's polynomial time algorithm based on ellipsoid method. And you will see that the algorithm is simple and easy to implement, and more details about this algorithm, like how to find the exact step size, can be found in Karmarkar's paper. So, with this we complete our discussion on interior point methods for linear programs. So, in particular we saw affine scaling method and Karmarkar's projective scaling method. The reason for studying interior point methods for linear program was that the simplex algorithm is not a exponential time algorithm, is not a polynomial time algorithm, it is a exponential time algorithm, and therefore, there is a need to design algorithms for linear programs which are polynomial time algorithms, and interior point methods are one of the approaches which ensure that the algorithms for solving linear programs are polynomial time. In fact, Karmarkar's algorithm has a better complexity compared to Khachiyan's algorithm for solving linear programs. Affine scaling algorithm which we studied is not a polynomial time algorithm, but nevertheless it is a simple algorithm and can be used for solving linear programs. So, this completes our discussion on linear programs. We now move on to constraint optimization problems and study some of the algorithms which could be useful for solving constraint optimization problems.